All right, so today we are going to continue our conservation of mass notes, part 3. So we're still focused on that standard. The properties of matter are determined by the arrangement of atoms. And we're really going to get pretty deep into that topic today with an I can statement of, I can explain the law of conservation of mass by showing how the total mass of substances mixed together won't change while their properties may or may not. So there's two types of changes in matter that we need to discuss. One is a physical change and one is a chemical change. When a substance goes through a physical change, the substance does not turn into a different substance. No new substance is made. Examples of this would be squashing a marshmallow, where you're changing the shape of the marshmallow, but the atoms that make it up are not being altered in any way. And when I say atoms, I'm really talking about the bonds between the atoms that makes marshmallow what it is. Other examples of things that you could do to a substance that would not change its atomic structure are bending, crushing, breaking, cutting, melting, freezing, boiling, any of those. So now we talk about chemical change, which a chemical change is also known as a chemical reaction. And this is when you do have a different or new substance formed from changes that happen to the atomic structure of the original substance or substances. An example now with a marshmallow is that when we make s'mores, we are actually sticking that marshmallow into a campfire, and the brown covering or coating of that marshmallow is actually caramel, and so that is a different substance that has formed, and the atomic structure, the bonds between those atoms have been altered. So now on your notes, you have the same diagram, and what I would like you to do is to circle the ones that you think represent a physical change. Leave alone the ones that you think are a chemical change, and we will discuss this when you come back to school on Tuesday. So in talking about chemical reactions or chemical changes, we also need to talk a little bit more deeply about chemical bonding, the bonds between atoms. And in class, we recently have just talked about the electrons and the energy levels of electrons. And so we've discussed whether atoms are happy or unhappy, and that has to do with how many electrons are on the outer energy level. And there is such thing as an octet rule. So over here I have linked a YouTube video that is a gentleman playing a guitar, and he is singing a song that reviews what we've studied so far about electrons on the energy level, but also takes you into understanding what the octet rule is. So once you are done taking these notes, I would like you to link to that video and watch that song and make sure that you're understanding what's in it. And then you can use that information to do the example problem down here. I want you to draw a diagram of sodium chloride. Sodium being Na, the element Na, and chloride being Cl. When those are chemically combined, form salt. And so what I would like you to do is draw a separate diagram for each one of those elements and look at how many electrons are on the outer energy level and kind of apply that octet rule and see if you think electrons would be shared between those atoms, given one gives another electrons, or received, one is accepting electrons, to make both of those a more complete energy level on the outer side of that atom. When you observe a chemical change, you might observe some things. And so these are clues, indicators that that's what you're observing as a chemical reaction. So some things might be bubbles. Bubbles are showing usually that there's a release of gas. And then another change would be temperature change. There are two types of temperature change, and it's usually a quick temperature change that happens. And one is endothermic, which is where the thermal energy, is absorbed by the substance. And then there's exothermic, which is where the energy is released by the substances. Another change that you might notice through observation is a quick color change of a substance. So other than making observations right away that might indicate a chemical change, if you have the ability to test some of the properties afterwards, after a chemical change takes place, you might notice differences, or you would notice differences in the physical and chemical properties of that different substance that was created. For example, if you take iron, once iron has had a chemical reaction with oxygen, it would end up rusting. And then you have a metal that used to be shiny and reflect light that no longer is going to do that. So it's lost its luster. There has been a color change as well. Freezing and melting point of that would be different. A substance, the boiling point, texture, those are just examples of the properties that the original substance might have had certain boiling points, certain freezing points, textures, etc. But then once two substances go through a chemical change together, the different substances created, those properties will have now changed. So really, what does the law of conservation of mass state? Well, here it is in my own words. You're going to see it several different ways between the book and other papers that we do, and etc. But during a physical or chemical reaction, the amount of matter is the same. That's telling you that the amount of atoms that are at the beginning of a reaction and then at the end after the reaction, those are the same. So we haven't lost any atoms, like disappeared, and we haven't gained any atoms. And even though the matter might look different or have different physical properties, chemical properties after a chemical reaction, the amount of matter will still be the same. So basically, matter cannot be created, destroyed, but it can change. However, the amount of mass. I like to think of a metaphor. Actually, this is Mr. Weaver's metaphor that I stole. He likes to think of the law of conservation of mass kind of like the middle school changing classes when the bell rings. And this is obviously excluding any students coming in or out of the school. But basically, if you're just considering middle school in general and the interior of the middle school, we all sit in class, but when the bell rings, everyone is moving and shifting places. So we've got some change going on. However, the number of bodies in the school is the same. Kind of a metaphor that you can think about when you think about the law of conservation of mass. Now, a lot of people have trouble observing the law of conservation of mass, so they often wonder, is it always true, or are there some times where it's not true? And the reality is that yes, the law is always true, but yes, it is hard to observe. The reason why sometimes it can be hard to observe is because sometimes you're observing it in an open system. And actually, most of the time, you're observing it in an open system. So what is an open system? A system where you've set up an experiment where matter can come into or out of a system. So therefore, if you're trying to measure how much mass the system has before a physical or chemical change takes place, and then you measure it afterwards, it's different because matter may have been able to escape during your experiment or come in during your experiment. And so that gives people the wrong impression that matter can just disappear or matter can just appear. An example of this is boiling water. You put a pot on the stove and you boil some water. It gets to a certain temperature where that water is then going to turn into a gas called water vapor. And because that water vapor is going to leave the pot if you don't have a lid and a very tight covered lid, then you are going to, it's going to seem like the water is going to decrease and decrease and decrease over time. And that could give someone the wrong impression that those atoms just disappeared when the boiling took place. So then what's happening is your system isn't just the pot, it's actually the house. If the windows are open, then it's actually the area around the house. So the system can kind of go on and go on and go on. So when we experiment in class, what we like to do is set up a closed system so that you can measure before, measure after, and note that the amount of matter will be the same. However, you can make observations on when it's different. All right, so I apologize if that cut out. I had a visitor, and so I paused it, but we're back together now. So I think I talked about a closed system a little bit, but that's where you can, it's basically a closed container. That's what you need to think about. And we will do experiments in here so that you can observe and prove to yourself the law of conservation of mass. And so we'll look at some physical changes within a closed system and some chemical changes within a closed system and look at the mass before and after and also make some observations about the properties that have changed or not changed as we've done those changes. So as I talked also earlier, you have to remember that there's some closed systems that may not seem like closed systems. For example, I like this diagram right here because it kind of reminds me that Earth and the on top of the Earth and the air above the Earth is kind of a closed system in itself. Energy comes in, but not a lot of matter comes in, and so therefore it's kind of its own closed system. So also in thinking that the solar system is kind of like a closed system, and then beyond that is the galaxy, and beyond that is the universe. So the overall thinking is that a huge closed system is the universe, and the matter that is inside the universe is basically what is here, and the matter that is not inside the universe will not be in the universe, if that makes any sense. All right, so we need to compare now compounds and mixtures. The biggest thing you need to know about a compound is that it is a chemically combination of two or more elements in a set ratio. So compounds occur due to a chemical reaction where atoms have been broken and new ones have, bonds between atoms have been broken and new ones have been formed, and therefore you have a compound. If you think about table salt, which again we talked earlier is NaCl, always, table salt is a compound, it always has 39.3% of its mass is sodium and 60.7% is chlorine. Otherwise, it is not table salt. Another example I like to think about is table sugar. And this is because it's important to understand that when atoms are combined, their physical properties that we most commonly think about when we think about those types of elements may not show. For example, table sugar is C12H22O11. However, when you combine those, those three elements don't necessarily represent like they would if they were separate. Carbon is usually a black substance. Hydrogen is usually a gas, so is oxygen. But table sugar is neither black or gaseous. So again, when those chemical reactions take place and the bonds between the atoms change due to electrons being given or shared or taken in a different way, we are creating a different substance that doesn't have the same physical properties. Okay. Mixtures. Mixtures are different from chemical I'm sorry, from compounds